Picture this, a star so massive that it could fit 1.3 million Earths inside it, burning at temperatures hotter than anything we could ever imagine. This isn't just any star, it's the Sun, the heart of our solar system and the very reason life exists on our planet. But what if I told you that the Sun is more than just a glowing ball of light in the sky? It's a cosmic powerhouse, a timekeeper, and even a storyteller of ancient myths. Today, we're diving into 25 mind-blowing facts about the Sun that will leave you in awe of its sheer power and mystery. From its unimaginable core temperatures to its role in shaping the future of humanity, this journey will reveal just how incredible our star truly is. So, buckle up and get ready to explore the wonders of the Sun, because by the end of this video, you'll never look at it the same way again. Let's begin. Now, let's dive into the heart of the Sun's incredible power. The Sun is essentially a massive nuclear reactor, but instead of using uranium or plutonium, it relies on something far more abundant: hydrogen. Deep within its core, the Sun performs a process called nuclear fusion, where hydrogen atoms are squeezed together under immense pressure and heat to form helium. This process releases an unimaginable amount of energy. To put it into perspective, every second, the Sun converts around 600 million tons of hydrogen into helium, releasing energy equivalent to billions of nuclear bombs exploding simultaneously. That's right, billions. This energy radiates outward, providing the light and heat that sustain life on Earth and power the entire solar system. It's a process so vast and powerful that it's almost impossible to fully comprehend, yet it's happening right now, fueling the very star that keeps us alive. Now, shifting our focus to the Sun's core, we encounter temperatures that defy imagination. At the heart of our star, the core reaches a staggering 15 million degrees Celsius. To put that into perspective, the hottest temperature ever recorded on Earth was a mere 56.7 degrees Celsius in Death Valley, California. That's less than a fraction of what the Sun's core experiences. Even the Earth's own core, which reaches around 6,000 degrees Celsius, pales in comparison. This unimaginable heat is the driving force behind nuclear fusion, the process that powers the Sun. Without this extreme temperature, the hydrogen atoms in the Sun's core wouldn't have enough energy to collide and fuse into helium, releasing the energy that lights up our solar system. It's a reminder of just how extreme and awe-inspiring the conditions are within the star that gives us life. Now, let's turn our attention to the Sun's incredible gravitational force, the invisible hand that keeps our solar system in perfect harmony. The Sun's gravity is so powerful that it holds everything in its orbit, from the tiniest asteroid to the largest planet. Without this gravitational pull, the planets would drift off into the vastness of space, and the solar system as we know it would cease to exist. What makes the Sun's gravity so dominant? It all comes down to its immense mass. The Sun accounts for a staggering 99.8% of the entire solar system's mass. To put that into perspective, if you gathered every planet, moon, asteroid, and comet in the solar system, their combined mass would still be just a tiny fraction compared to the Sun. This overwhelming mass creates a gravitational field strong enough to keep all these celestial bodies in their orbits, moving in a delicate cosmic dance that has lasted for billions of years. Think of the Sun as the anchor of the solar system. Its gravity not only keeps the planets in line but also influences their paths, ensuring they follow elliptical orbits rather than flying off in straight lines. Even the farthest reaches of the solar system, like the icy comets in the Oort cloud, are held in place by the Sun's gravitational grip. It's a reminder of just how central the Sun is to the structure and stability of our cosmic neighborhood. As we marvel at this gravitational masterpiece, it's worth noting that the Sun's influence extends far beyond just holding things together. Its gravity also plays a key role in shaping the orbits of spacecraft, enabling missions to explore distant worlds. Without the sun's gravitational pull, humanity's journey into space would be far more challenging, if not impossible. So, the next time you look up at the sky, remember that the sun's gravity is the silent force that keeps our solar system spinning in perfect harmony. Now, shifting our gaze to the speed of light, let's explore a fascinating aspect of the sun's relationship with Earth. The sunlight that warms our planet and brightens our days doesn't reach us instantly. In fact, it takes about 8 minutes and 20 seconds for light to travel the staggering distance of 93 million miles from the sun to Earth. This means that when you look up at the sun, you're actually seeing it as it was over 8 minutes ago. It's a reminder that even light, the fastest thing in the universe, has its limits when it comes to crossing the vastness of space. This delay has profound implications, especially for space exploration. Imagine sending a spacecraft to study the sun or another planet. The time it takes for light to travel means that the data we receive from these missions is always slightly out of date. For example, if a spacecraft detects a solar flare, by the time that information reaches Earth, the event has already happened. This delay requires scientists to account for the time lag when planning missions and interpreting data, ensuring that decisions are made with the most accurate and timely information possible. But the speed of light isn't just a challenge for space exploration, it's also a fundamental limit that shapes our understanding of the universe. It defines how quickly we can communicate across vast distances, whether it's with a rover on Mars or a probe at the edge of the solar system. Every command sent and every signal received must account for this delay, making space exploration a carefully timed and meticulously planned endeavor. So, the next time you step outside and feel the sun's warmth on your skin, remember that you're experiencing a moment from the past. The light you see and the heat you feel began its journey 8 minutes earlier, a testament to the incredible scale of our solar system and the delicate dance of time and distance that connects us to our star. Now, turning to the life cycle of our star, let's consider the sun's age and its future. The sun, which has been shining for about 4.6 billion years, is currently in what astronomers call its main sequence phase. This means it's in the prime of its life, steadily converting hydrogen into helium through nuclear fusion. But like all stars, the sun won't shine forever. Scientists estimate it has roughly 5 billion years left before it exhausts its hydrogen fuel. When that time comes, the sun will enter a dramatic new phase. As it runs out of hydrogen, its core will contract, causing the outer layers to expand and cool. The sun will transform into a red giant, growing so large that it could engulf Mercury, Venus, and possibly even Earth. During this phase, the sun's surface will cool, giving it a reddish hue, but its core will grow hotter, triggering the fusion of heavier elements like helium. Eventually, the sun will shed its outer layers, creating a beautiful planetary nebula. What remains will be its dense core, now a white dwarf, a small, incredibly dense object that will slowly cool over billions of years. This final stage marks the end of the sun's active life, leaving behind a faint glow in the cosmos. So, while the sun is middle-aged now, its eventual transformation reminds us of the dynamic and ever-changing nature of the universe. Every star has a story, and the sun's is far from over. Now, shifting our gaze to the sun's ever-changing surface, we uncover a world of constant motion and activity. Unlike the calm, steady appearance we see from Earth, the sun's surface is a swirling, dynamic environment. This is where solar flares, sunspots, and coronal mass ejections take center stage, each playing a role in the sun's dramatic behavior. Solar flares are sudden, intense bursts of energy that erupt from the sun's surface, releasing as much energy as 1 billion hydrogen bombs in just minutes. These flares are often accompanied by sunspots, which are darker, cooler areas on the sun's surface caused by intense magnetic activity. Sunspots can grow to sizes larger than Earth and often appear in pairs or groups, marking regions where the sun's magnetic field is particularly strong. But the drama doesn't stop there. Coronal mass ejections, or CME, are massive eruptions of charged particles and magnetic fields that the Sun hurls into space. These events can send billions of tons of solar material racing toward Earth at incredible speeds. When these particles interact with our planet's magnetic field, they create stunning auroras, but they can also disrupt satellites, power grids, and communication systems. The impact of these solar phenomena on Earth is profound. Solar flares and CMEs can interfere with GPS signals, disrupt radio communications, and even pose risks to astronauts in space. Understanding these events is crucial for protecting our technology and infrastructure, as well as planning future space missions. So, while the Sun's surface may seem distant, its constant motion and explosive activity remind us of its powerful influence on our daily lives. From dazzling auroras to technological disruptions, the Sun's dynamic surface is a testament to the intricate connection between our star and our planet. Now, turning to the Sun's magnetic field, we uncover one of the most fascinating and intricate aspects of our star. Unlike Earth's relatively stable magnetic field, the Sun's is a dynamic, ever-changing force that shapes much of its behavior. This magnetic field is responsible for creating sunspots, driving solar flares, and even influencing the solar wind that flows through our solar system. At the heart of this complexity is the Sun's internal structure. Deep within its core, the Sun generates a magnetic field through the motion of charged particles, a process known as the solar dynamo. This magnetic field extends outward, twisting and tangling as it interacts with the Sun's rotating layers. The result is a magnetic landscape that is anything but simple. One of the most striking features of the Sun's magnetic field is its 11-year cycle, known as the solar cycle. During this period, the Sun's magnetic poles gradually flip, with the north and south poles swapping places. This reversal is a natural part of the Sun's behavior and is closely tied to the rise and fall of solar activity. At the peak of the cycle, known as solar maximum, sunspots and solar flares become more frequent, while at solar minimum, the Sun's surface appears calmer. But why does this happen? The answer lies in the Sun's differential rotation. The Sun rotates faster at its equator than at its poles, causing its magnetic field lines to stretch and twist over time. This twisting builds up energy, which is eventually released in the form of solar flares and coronal mass ejections. These events are not just spectacular to observe, they also play a crucial role in shaping space weather and its effects on Earth. Understanding the Sun's magnetic field is key to predicting solar activity and its impact on our planet. From protecting satellites to ensuring the safety of astronauts, this knowledge helps us navigate the challenges posed by our star's dynamic nature. So, while the Sun's magnetic field may be invisible to the naked eye, its influence is anything but subtle, reminding us once again of the intricate connection between our star and our world. Now, shifting our gaze to the Sun's atmosphere, we encounter one of the most puzzling mysteries in solar science. While the Sun's surface, known as the photosphere, reaches temperatures of around 5,500 degrees Celsius, its outer atmosphere, the corona, soars to a staggering 1 to 3 million degrees Celsius. This dramatic temperature difference defies our basic understanding of heat transfer, creating a paradox that has baffled scientists for decades. So, why is the Sun's atmosphere so much hotter than its surface? One leading theory points to the Sun's magnetic field as the key player. The corona is threaded with magnetic loops and arcs that store immense amounts of energy. When these magnetic fields become twisted or tangled, they can suddenly release that energy in the form of nanoflares, tiny but frequent bursts of heat. Over time, these nanoflares could collectively heat the corona to its extreme temperatures. Another theory suggests that waves of energy, called magnetohydrodynamic waves, travel from the Sun's surface into its atmosphere. These waves carry energy that dissipates as heat, potentially explaining the corona's scorching temperatures. However, scientists are still working to fully understand how this process works and how much it contributes to the overall heating. The mystery of the Sun's corona isn't just an academic curiosity, it has real-world implications. The corona's extreme heat drives the solar wind, a stream of charged particles that flows throughout the solar system. Understanding how the corona is heated could help us better predict solar storms and their effects on Earth's technology and infrastructure. As we continue to study the Sun, missions like the Parker Solar Probe are bringing us closer to solving this enigma. By flying through the corona and collecting data, this groundbreaking mission is shedding light on the mechanisms behind the Sun's atmospheric heating. The Sun's corona reminds us that even the most familiar objects in the universe can hold profound secrets. As we unravel these mysteries, we gain not only a deeper understanding of our star, but also a greater appreciation for the intricate forces that shape our solar system. Now, turning to the shape of our star, we uncover another fascinating detail about the Sun. It's not a perfect sphere. While it may appear round to the naked eye, the Sun is actually slightly flattened at its poles and bulges at its equator. This unique shape is caused by its rotation. Just like a spinning ball of dough flattens out, the Sun's rapid spin, completing a full rotation in about 25 days at the equator, stretches it into this slightly squashed form. This shape, known as an oblate spheroid, has important implications for the Sun's gravitational field and solar dynamics. The flattening at the poles and the bulge at the equator mean that the Sun's gravity isn't perfectly uniform. This uneven gravitational pull influences the movement of plasma and magnetic fields on the Sun's surface, contributing to the complex patterns of solar activity we observe, such as sunspots and solar flares. Interestingly, this shape also affects how the Sun interacts with its surroundings. The equatorial bulge creates a stronger gravitational pull in that region, which can influence the orbits of planets and other objects in the solar system. While the effect is subtle, it's a reminder of how even the smallest details of the Sun's structure can have far-reaching consequences. The Sun's imperfect shape is a testament to the dynamic forces at work within our star. It's not just a static ball of gas, but a constantly evolving, spinning powerhouse that shapes the very fabric of our solar system. As we continue to study these subtle features, we gain a deeper appreciation for the intricate balance of forces that govern our cosmic neighborhood. Now, shifting our focus to the Sun's energy, we uncover a surprising truth: its energy output isn't constant. While it may seem like the Sun shines with unwavering brightness, its energy production actually fluctuates over time. These subtle changes, though small, can have significant effects on Earth's climate and weather patterns. This variation in energy output is tied to something called solar cycles, which occur over roughly 11 years. During a solar cycle, the Sun goes through periods of high activity, known as solar maximum, and low activity, called solar minimum. During solar maximum, the Sun's surface becomes more active, with increased sunspots, solar flares, and coronal mass ejections. These events release more energy, slightly boosting the Sun's overall output. Conversely, during solar minimum, the Sun becomes quieter and its energy output decreases. These fluctuations, while minor, can influence Earth in surprising ways. For instance, during periods of high solar activity, the increased energy can warm the upper layers of Earth's atmosphere, affecting satellite orbits and communication systems. On the other hand, periods of low solar activity have been linked to cooler global temperatures, such as during the Little Ice Age in the 17th century, when a prolonged solar minimum coincided with unusually cold weather. The Sun's energy output also plays a role in shaping Earth's climate over longer timescales. Scientists study these solar cycles to better understand how they interact with other factors like greenhouse gases to influence global temperatures. While the Sun's variability isn't the sole driver of climate change, it's an important piece of the puzzle. As we continue to monitor these solar cycles, we gain valuable insights into the delicate balance between the sun's energy and Earth's environment. It's a reminder that even the smallest changes in our star can ripple across the solar system, shaping the world we live in. Now, turning to the very fabric of the sun itself, we find that it's composed almost entirely of two elements, hydrogen and helium. In fact, hydrogen makes up about 74% of the sun's mass, while helium accounts for roughly 24%. Together, these two elements form the backbone of our star, fueling its incredible energy production and shaping its structure. But what about the remaining 2%? While it may seem small, this tiny fraction is made up of heavier elements like oxygen, carbon, nitrogen, and iron. These elements, though present in trace amounts, play a crucial role in the sun's dynamics. For instance, they influence the sun's internal processes, such as how heat is transferred from the core to the surface. They also contribute to the sun's overall density and help scientists understand the history of our solar system, as these heavier elements were forged in the hearts of ancient stars long before the sun was born. The dominance of hydrogen and helium isn't just a quirk of the sun, it's a reflection of the universe itself. These two elements are the most abundant in the cosmos, created in the aftermath of the Big Bang. The sun's composition, then, is a snapshot of the universe's earliest moments, preserved in the heart of our solar system. Understanding the sun's makeup isn't just about numbers, it's about grasping how these elements work together to create the star we depend on. Hydrogen, for example, is the fuel for nuclear fusion, the process that powers the sun. Helium, on the other hand, is the byproduct of this fusion, accumulating in the sun's core over billions of years. Together, they form a delicate balance that keeps the sun shining brightly, providing the energy that sustains life on Earth. As we peel back the layers of the sun's composition, we gain a deeper appreciation for the intricate processes that make our star what it is. It's a reminder that even the simplest elements, when combined in the right way, can create something truly extraordinary. Now, shifting our gaze to the sun's outer influence, we encounter the solar wind, a constant stream of charged particles racing outward from the sun at incredible speeds. This solar wind isn't just a gentle breeze, it's a powerful force that shapes the very environment of our solar system. As these particles travel through space, they create what's known as the heliosphere, a vast protective bubble that extends far beyond the orbits of the planets. The heliosphere acts like a cosmic shield, deflecting harmful cosmic rays and interstellar particles that could otherwise bombard the solar system. Without this protective barrier, life on Earth would face far greater risks from high-energy radiation. The solar wind doesn't just stop at the edge of the heliosphere, though. It continues to push against the interstellar medium, the thin gas and dust that fills the space between stars, carving out a boundary where the sun's influence meets the broader galaxy. This boundary, called the heliopause, marks the edge of the sun's domain. Beyond it lies the uncharted territory of interstellar space, where the solar wind's strength wanes and the influence of other stars begins to take hold. The heliosphere isn't static, it's constantly changing, shaped by the sun's activity and the pressure of the interstellar medium. During periods of high solar activity, the heliosphere expands while quieter phases cause it to contract. Understanding the solar wind and the heliosphere isn't just about mapping the boundaries of our solar system, it's about appreciating how the sun's energy extends far beyond what we can see. This invisible force not only protects us but also connects us to the larger cosmos, reminding us that even the smallest particles can have a profound impact on the universe around us. As we explore the sun's influence, we're reminded that its reach is far greater than the light and warmth it provides. The solar wind and the heliosphere are testaments to the sun's enduring power, shaping the environment of our solar system and safeguarding the delicate balance that makes life on Earth possible. Now, shifting our perspective to the sheer enormity of the sun, Let's try to wrap our minds around its staggering size. The Sun is so massive that it's almost impossible to fully grasp without some mind-bending comparisons. For starters, if you were to line up 1,300,000 Earths side by side, they would just about fill the volume of the Sun. That's right, our entire planet, with all its vast oceans, towering mountains, and sprawling continents, is just a tiny speck compared to the Sun's colossal scale. To put it another way, the Sun's diameter stretches an incredible 1,390,000 kilometers. That's more than 100 times the diameter of Earth. Imagine standing on the surface of the Sun, if you could survive the heat, and looking out across a landscape so vast that it would take light, traveling at 300,000 kilometers per second, about 4.5 seconds to cross from one side to the other. But the Sun's size isn't just about numbers, it's about the sheer dominance it holds over our solar system. Its immense gravitational pull keeps planets, asteroids, and comets in their orbits, and its energy output powers every aspect of life on Earth. When we talk about the Sun's size, we're not just discussing a star, we're talking about the heart of our cosmic neighborhood, a celestial giant that shapes everything around it. As we marvel at the Sun's size, it's worth reflecting on how this incredible scale influences our understanding of the universe. The Sun isn't just a star, it's a reminder of the vastness of space and the delicate balance that allows life to thrive on our tiny planet. And as we continue to explore the mysteries of our solar system, the Sun's size serves as a humbling reminder of just how small we are in the grand scheme of things. Now, turning to the Sun's unique rotation, we uncover another fascinating aspect of our star's behavior. Unlike Earth, which rotates uniformly, the Sun spins at different speeds depending on where you look. At its equator, the Sun completes a full rotation in about 25 days, but near its poles, it takes a slower 36 days. This phenomenon, known as differential rotation, is a result of the Sun being a massive ball of gas rather than a solid object. This uneven rotation has profound effects on the Sun's magnetic field and solar activity. As the Sun's layers rotate at varying speeds, its magnetic field lines become twisted and tangled over time. This twisting builds up energy, which eventually gets released in the form of solar flares, sunspots, and coronal mass ejections. These bursts of energy can have significant impacts on space weather, influencing everything from satellite communications to power grids on Earth. The differential rotation also plays a key role in the Sun's 11-year solar cycle. During this cycle, the Sun's magnetic field undergoes dramatic changes, flipping its polarity and driving periods of high and low solar activity. Understanding this rotation helps scientists predict solar storms and better prepare for their effects on our technology-dependent world. As we explore the Sun's differential rotation, we're reminded of how dynamic and complex our star truly is. It's not just a static ball of fire, it's a constantly churning, ever-changing force that shapes the environment of our solar system. And as we continue to study its behavior, we gain deeper insights into the intricate dance of energy and magnetism that powers our cosmic neighborhood. Now, shifting our focus to the life-giving power of the Sun, we arrive at a fact that underscores its profound importance to every living thing on Earth. The Sun's energy is the driving force behind the processes that sustain life as we know it. Without it, our planet would be a frozen, lifeless rock drifting through space. At the heart of this life-sustaining energy is photosynthesis, the remarkable process by which plants convert sunlight into chemical energy. This energy forms the foundation of the food chain, providing nourishment for plants, animals, and ultimately, humans. Every bite of food we eat, every breath of oxygen we take, traces its origins back to the Sun's radiant energy. But the Sun's influence doesn't stop there. It also powers Earth's weather systems, driving the movement of air and water across the planet. The Sun heats the Earth unevenly, creating temperature differences that generate wind and weather patterns. These patterns, in turn, shape our climate and influence everything from agriculture to the availability of fresh water. The sun also plays a critical role in the water cycle, the continuous movement of water between the Earth's surface and the atmosphere. Solar energy evaporates water from oceans, lakes, and rivers, forming clouds that eventually release rain or snow. This cycle ensures that water is distributed across the planet, supporting ecosystems and human societies alike. In every way, the sun is the ultimate source of life on Earth. Its energy fuels the processes that keep our planet vibrant and teeming with life. From the smallest blade of grass to the mightiest oak tree, from the tiniest microbe to the largest whale, every living thing depends on the sun's light and warmth. As we reflect on this incredible fact, we're reminded of just how interconnected our world is and how vital the sun is to our existence. It's not just a distant star, it's the very heartbeat of life on Earth. And as we continue to explore its mysteries, we gain a deeper appreciation for the delicate balance that makes our planet so unique. With this understanding, let's turn our attention to another fascinating aspect of the sun, its true color, which might surprise you. Now let's shed some light on a surprising truth about the sun, its color. Despite what our eyes might tell us, the sun doesn't actually shine with a yellow hue. In reality, the sun emits white light. This white light is a combination of all the colors of the rainbow, blending together to create what we perceive as pure, bright light. So why does the sun often appear yellow, especially during sunrise or sunset? The answer lies in Earth's atmosphere. As sunlight passes through the atmosphere, it interacts with tiny molecules and particles in the air. This interaction causes shorter wavelengths of light, like blue and violet, to scatter in all directions. This scattering effect, known as Rayleigh scattering, is also why our sky appears blue during the day. What's left after this scattering is the longer wavelengths of light, red, orange, and yellow, which travel more directly to our eyes. This is why the sun often looks yellow, particularly when it's low on the horizon. At sunrise and sunset, the light has to pass through even more of the atmosphere, intensifying this effect and sometimes giving the sun a deep orange or red appearance. This fascinating interplay between sunlight and Earth's atmosphere not only shapes how we see the sun, but also influences our perception of the world around us. It's a reminder that what we see isn't always the full story. Sometimes there's science behind the scenes, revealing truths that go beyond our everyday observations. With this new understanding of the sun's true color, let's move forward to explore another captivating aspect of our star, its future and how it will ultimately transform the solar system. Now let's journey into the distant future of our solar system and uncover what lies ahead for the sun. While it may seem like our star has been a constant presence in the sky, the truth is that the sun, like all stars, has a life cycle, and its future will dramatically reshape everything around it. In about 5 billion years, the sun will exhaust its hydrogen fuel, the very element it has been fusing into helium for billions of years. When this happens, the sun will begin to change in ways that will have profound effects on the entire solar system. Without the outward pressure of nuclear fusion to balance its immense gravity, the sun's core will contract and heat up while its outer layers expand outward. This transformation will turn the sun into a red giant, a phase where it will swell to hundreds of times its current size. During this red giant phase, the sun's outer layers will engulf the inner planets, including Mercury and Venus. Earth's fate is less certain. Some scientists believe our planet might escape being swallowed by the sun's expanding atmosphere, but even if it does, the intense heat will scorch its surface, rendering it uninhabitable. Oceans will evaporate and the atmosphere will be stripped away, leaving behind a barren, lifeless world. As the red giant phase comes to an end, the sun will shed its outer layers, creating a stunning planetary nebula. What remains will be the sun's core, now a dense, glowing ember known as a white dwarf. This white dwarf will no longer produce energy through fusion, but will instead slowly cool over trillions of years, fading into a dark, cold remnant of what was once the heart of our solar system. The outer planets, like Jupiter and Saturn, will likely survive this transformation, though their orbits may shift as the Sun loses mass. Moons and icy bodies in the outer solar system could experience dramatic changes, with some potentially becoming more habitable as the Sun's energy output evolves. This glimpse into the Sun's future reminds us that even the most stable and familiar elements of our universe are part of a grand, ever-changing cosmic story. As we continue to explore the wonders of our star, let's turn our attention to another fascinating phenomenon: how the Sun's solar flares can disrupt technology here on Earth. Now, shifting our focus to the Sun's more immediate impact on our daily lives, let's explore how its powerful solar flares can disrupt the technology we rely on. Solar flares are sudden, intense bursts of radiation from the Sun's surface, often accompanied by coronal mass ejections, which are massive clouds of charged particles hurled into space. While these phenomena are awe-inspiring, they can also pose serious challenges for modern technology. When a solar flare or coronal mass ejection reaches Earth, it interacts with our planet's magnetic field, creating geomagnetic storms. These storms can interfere with satellites orbiting Earth, disrupting GPS signals, satellite communications, and even causing malfunctions in their electronics. For example, in 1989, a powerful geomagnetic storm caused by a solar flare knocked out the power grid in Quebec, Canada, leaving millions without electricity for hours. This event highlighted just how vulnerable our infrastructure can be to the Sun's activity. Power grids are particularly at risk during intense solar activity. The influx of charged particles can induce electric currents in power lines, overwhelming transformers and other critical components. This can lead to widespread blackouts and costly damage. Similarly, communication systems, including radio signals and internet connectivity, can be disrupted, affecting everything from air travel to emergency services. One of the most dramatic examples of solar activity impacting Earth occurred in 1859, during what's known as the Carrington event. A massive solar flare caused telegraph systems across Europe and North America to fail, with some operators reporting sparks and even fires. If an event of this magnitude were to occur today, the consequences could be far more severe given our reliance on technology. To mitigate these risks, scientists and engineers are constantly monitoring the Sun's activity. Satellites like the Solar and Heliospheric Observatory, or SOHO, and the Parker Solar Probe provide real-time data, helping us predict and prepare for solar storms. By understanding the Sun's behavior, we can develop strategies to protect our technology and infrastructure, ensuring that we're better equipped to handle the Sun's unpredictable nature. As we continue to explore the Sun's influence on our world, let's turn our attention to another fascinating aspect of its power: how its immense gravity bends light, a phenomenon that has reshaped our understanding of the universe. Now let's dive into one of the most mind-bending aspects of the Sun's influence: how its immense gravity can actually warp the fabric of space and time. This phenomenon is rooted in Albert Einstein's theory of general relativity, which revolutionized our understanding of gravity. According to Einstein, massive objects like the Sun don't just pull on objects with a force, they actually bend the very fabric of spacetime around them. This curvature affects everything, including light itself. When light from distant stars passes near the Sun, its path isn't straight, it gets bent. Imagine spacetime as a stretched-out sheet and the Sun as a heavy ball placed in the middle. The ball creates a dip in the sheet, and any object rolling nearby, like light, will curve around it. This bending of light is known as gravitational lensing, and it's one of the most fascinating predictions of Einstein's theory. But how do we know this actually happens? The proof came during a total solar eclipse in 1919. British astronomer Arthur Eddington led an expedition to observe the eclipse, aiming to test Einstein's theory. During the eclipse, the moon blocked the sun's bright light, allowing Eddington to photograph the positions of stars near the sun's edge. What he found was astonishing. The stars appeared slightly shifted from their usual positions, exactly as Einstein had predicted. This shift was caused by the sun's gravity bending the starlight as it passed by. This groundbreaking discovery not only confirmed Einstein's theory, but also changed the way we understand the universe. It showed that gravity isn't just a force, it's a curvature of space-time itself. Today, gravitational lensing is a powerful tool in astronomy, helping scientists study distant galaxies, dark matter, and even the expansion of the universe. As we marvel at the sun's ability to bend light, let's shift our gaze to another incredible fact: how the sun's energy could power humanity for billions of years, offering a glimpse into a future fueled by the stars. Now, let's explore a fact that could reshape the future of humanity: how the sun's energy holds the potential to power our world for billions of years. The sun is an endless source of energy, radiating an astonishing amount of power every second. In fact, the energy it emits in just 1 hour could meet the entire world's energy needs for an entire year. That's how immense its potential is. Solar energy, harnessed through technologies like solar panels, offers a clean, renewable way to tap into this incredible resource. Unlike fossil fuels, which are finite and harmful to the environment, solar energy is abundant and sustainable. By capturing even a tiny fraction of the sun's energy, we could meet global energy demands indefinitely, reducing our reliance on polluting energy sources and combating climate change. Imagine a world where every rooftop, desert, and open space is equipped with solar panels, silently converting sunlight into electricity. This vision isn't just science fiction, it's a tangible possibility. Advances in solar technology are making it more efficient and affordable, bringing us closer to a future powered entirely by the sun. But the potential doesn't stop there. Scientists are also exploring ways to replicate the sun's energy production here on Earth through nuclear fusion. If successful, fusion could provide a nearly limitless supply of clean energy, mimicking the processes that power the sun itself. While this technology is still in development, it represents a promising step toward a sustainable energy future. As we look to the stars, it's clear that the sun isn't just a source of light and warmth, it's a key to humanity's survival and progress. By harnessing its energy, we can create a cleaner, brighter future for generations to come. And with that, let's turn our attention to the sun's dynamic surface, where constant movement and activity shape the star we know and depend on. Now, shifting our gaze to the sun's surface, we uncover a fascinating detail that often goes unnoticed: its granular texture. The sun's surface isn't smooth or uniform. Instead, it's covered in a patchwork of tiny, cell-like structures called granules. These granules are the result of convection currents, where hot plasma rises from the sun's interior, cools slightly at the surface, and then sinks back down. This constant churning creates a dynamic, ever-changing landscape that's both mesmerizing and scientifically significant. Each of these granules is enormous, roughly the size of the state of Texas. To put that into perspective, imagine a single granule stretching across hundreds of miles. Despite their size, these granules are relatively short-lived, lasting only about 8 to 20 minutes before new ones form. This rapid turnover gives the sun's surface a boiling, almost turbulent appearance, like a pot of water on the verge of boiling over. What's truly remarkable is how these granules reveal the sun's inner workings. They act as windows into the star's core, showing us how energy is transported from the interior to the surface. Without these granules, the sun's heat would remain trapped, unable to radiate into space. So, while they may seem like mere surface details, they play a crucial role in the sun's energy dynamics. As we marvel at this granular tapestry, It's a reminder of how even the smallest features of the sun hold immense significance. And with that, let's turn our attention to the sun's solar cycles, where its activity ebbs and flows in a rhythm that shapes the very fabric of our solar system. Now, as we delve deeper into the sun's rhythmic dance, we encounter one of its most fascinating patterns, the solar cycle. Every 11 years, the sun undergoes a dramatic transformation, shifting between periods of intense activity and relative calm. This cycle, known as the solar maximum and solar minimum, shapes not only the sun's behavior but also the environment of our entire solar system. During the solar maximum, the sun becomes a hive of activity. Sunspots, solar flares, and coronal mass ejections become more frequent and powerful. These events are driven by the sun's magnetic field, which becomes increasingly tangled and chaotic during this phase. The result is a surge in space weather which can have profound effects on Earth. For instance, powerful solar flares can disrupt satellite communications, interfere with GPS systems, and even pose risks to astronauts in space. Auroras, those stunning light displays near the poles, also become more vivid and widespread during this time. On the other hand, the solar minimum is a period of quiet. Sunspots become rare and solar activity diminishes significantly. While this might sound like a peaceful phase, it's not without its own challenges. The reduced solar wind during this time allows more cosmic rays to penetrate the solar system, which can affect both space missions and Earth's atmosphere. Interestingly, some scientists believe that prolonged solar minima, like the historic Maunder minimum in the 17th century, may have contributed to cooler global temperatures, though this remains a topic of ongoing research. What's truly remarkable is how this 11-year cycle reflects the sun's internal dynamo, a complex interplay of magnetic fields and plasma currents deep within its core. By studying these cycles, scientists gain valuable insights into the sun's behavior and its influence on space weather, helping us better prepare for its effects on our technology and climate. As we reflect on this rhythmic ebb and flow, it's clear that the sun's cycles are more than just a celestial phenomenon. They're a reminder of the intricate connections between our star and life on Earth. And with that, let's turn our attention to the sun's profound role in ancient cultures, where it was revered as a symbol of power, life, and divinity. Now, as we journey back in time, we uncover the profound reverence ancient civilizations held for the sun. For countless cultures, the sun was far more than a celestial body. It was a divine force, a life-giver, and a symbol of power. The Egyptians, for instance, worshipped the sun as Ra, the god who sailed across the sky each day, bringing light and life to the world. Temples were built in his honor, aligned precisely with the sun's movements, and the pharaohs themselves were seen as his earthly representatives. The Great Pyramid of Giza, one of the 7 wonders of the ancient world, is thought to have been constructed with solar alignments in mind, reflecting the sun's central role in their cosmology. Similarly, the Aztecs revered the sun as Tonatiuh, a deity whose energy sustained the universe. Their intricate calendar system, the Sun Stone, is a masterpiece of ancient astronomy, depicting the sun at its center, surrounded by symbols of time and cosmic cycles. The Aztecs believed that the sun required nourishment to continue its journey across the sky, leading to rituals and offerings to ensure its survival. Even their architecture, like the Templo Mayor in Tenochtitlan, was designed to honor the sun and mark its pivotal moments, such as the solstices and equinoxes. In ancient Greece, the sun was personified as Helios, who rode his chariot across the sky each day. The Greeks also developed sophisticated astronomical tools, like the Antikythera mechanism, to track the sun's movements and predict celestial events. Meanwhile, in India, the sun was worshipped as Surya, a deity associated with health, vitality, and enlightenment. The sun's influence extended to their art, literature, and even medicine, with practices like Surya Namaskar or sun salutations still widely practiced today. These ancient cultures, though separated by geography and time, shared a common thread: their deep connection to the sun. It shaped their worldviews, inspired their greatest achievements, and left an indelible mark on human history. As we reflect on their legacy, it's clear that the sun's role in ancient cultures was not just about worship, it was about understanding humanity's place in the cosmos. And with that, let's turn our gaze to the sun's influence on human health, where its rays continue to shape our lives in profound ways. Now, as we shift our focus from the sun's historical significance to its modern-day impact, let's explore how this celestial giant influences our health in ways both profound and subtle. The sun's rays are not just a source of light and warmth, they play a critical role in our physical and mental well-being. One of the most well-known benefits of sunlight is its ability to help our bodies produce vitamin D, a nutrient essential for bone health, immune function, and even mood regulation. Just a few minutes of sun exposure each day can kickstart this process, making it a natural and accessible way to support overall health. However, the sun's influence isn't without its risks. Ultraviolet or UV radiation from the sun can damage our skin, leading to sunburn, premature aging, and even an increased risk of skin cancer. This is why it's crucial to strike a balance, enjoying the sun's benefits while protecting ourselves with sunscreen, protective clothing, and shade when necessary. The key is moderation, as too much or too little sunlight can have significant consequences for our health. Beyond its physical effects, the sun also plays a vital role in regulating our circadian rhythms, the internal clock that governs our sleep-wake cycles. Exposure to natural light during the day helps keep this clock in sync, promoting better sleep and overall energy levels. Conversely, a lack of sunlight, especially during the darker months, can disrupt these rhythms, leading to conditions like seasonal affective disorder or SAD, which affects mood and energy levels. This highlights the sun's deep connection to our mental health, as its light can uplift our spirits and combat feelings of fatigue or depression. In essence, the sun is a powerful ally in maintaining our health, but it demands respect. By understanding its dual nature, its ability to heal and harm, we can harness its benefits while minimizing its risks. And as we continue to uncover the sun's many roles in our lives, we're reminded of its enduring influence, not just on our planet, but on each of us individually. With that in mind, let's turn our attention to the sun's role in space exploration, where its energy and gravity continue to propel humanity's quest to understand the cosmos. Now, as we venture into the final frontier of our journey, let's explore how the sun's immense power and gravitational pull have become indispensable tools in humanity's quest to explore the cosmos. The sun isn't just a distant star, it's a driving force behind our ability to navigate and study the solar system. Its energy and gravity play a crucial role in propelling spacecraft, enabling missions that push the boundaries of our understanding. Take, for example, the Parker Solar Probe, a groundbreaking mission designed to study the sun closer than ever before. Launched in 2018, this spacecraft is on a daring journey to touch the sun, flying through its scorching outer atmosphere known as the corona. By braving temperatures of over 1 million degrees Celsius, the Parker Solar Probe is uncovering secrets about solar winds, magnetic fields, and the sun's dynamic behavior, information that could revolutionize our understanding of space weather and its impact on Earth. But the sun's influence doesn't stop there. Its gravity acts as a cosmic slingshot, a technique known as a gravity assist, which spacecraft use to gain speed and change direction without expending extra fuel. Missions like Voyager 1 and 2, which have traveled beyond our solar system, relied on this method to reach their incredible destinations. Even missions to distant planets like Jupiter and Saturn have harnessed the sun's gravitational pull to navigate the vastness of space more efficiently. The sun's energy is also a vital resource for spacecraft. Solar panels, which convert sunlight into electricity, power many of our probes and satellites, enabling them to operate for years in the harsh environment of space. Without the Sun's light, missions like the Mars rovers or the International Space Station would struggle to function, highlighting just how interconnected our exploration efforts are with this celestial powerhouse. As we reflect on the Sun's role in space exploration, it's clear that this star is more than just a source of light and warmth. It's a partner in our journey to uncover the mysteries of the universe. From powering our spacecraft to guiding their paths, the Sun continues to shape humanity's reach into the cosmos, reminding us of its enduring influence on both our planet and our ambitions. And with that, we've reached the end of our exploration of 25 mind-blowing facts about the Sun, a journey that has illuminated just how extraordinary our star truly is. As we bring our journey through the wonders of the Sun to a close, let's take a moment to reflect on the incredible facts we've uncovered. From its role as a colossal nuclear reactor to its gravitational dominance over the solar system, the Sun is truly the heart of our cosmic neighborhood. We've explored how its energy fuels life on Earth, how its magnetic field shapes space weather, and even how its future will transform the solar system as we know it. Each fact reveals just how vital this star is not just to our planet, but to the entire universe. The Sun's influence stretches far beyond its fiery surface. It powers our technology, inspires ancient myths, and even guides our spacecraft through the vastness of space. Its light, heat, and gravity are woven into the fabric of our existence, reminding us of the profound connection between humanity and the cosmos. Whether it's the mystery of its scorching corona or the beauty of its solar flares, the Sun continues to captivate and challenge us, driving our curiosity and ambition to explore further. Now it's your turn to join the conversation. Which of these 25 mind-blowing facts about the Sun amazed you the most? Was it the sheer scale of its energy output, the way its gravity bends light, or perhaps its role in shaping ancient cultures? Share your thoughts in the comments below, and let's keep the discussion alive. If you enjoyed this journey through the wonders of our star, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss out on exploring the mysteries of the universe. Together, let's keep reaching for the stars and uncovering the secrets of the cosmos. Thanks for watching, and until next time, keep looking up.